dear me, you in your aeroplane have an interrogator. So it works on interrogation and response. There's equipment on the ground which responds. It transmits a response, so it's called a transponder. Transmits a response. Your aeroplane interrogates, and it interrogates by sending a series of pairs of pulses. So something like that. Now, the timing between the pulses is fixed, but the space between the pairs of pulses is changing all the time. It's called a random PRF, pulse repetition frequency, random PRF, or you might see the word jittered PRF. So you send this down. This device here waits 50 microseconds before it replies. And then it sends back exactly the same pattern that you sent. Got that the wrong way around, haven't I? But never mind. It sends back exactly the same pattern. Now, this transponder, of course, is responding to a lot of other airplanes. You're not the only airplane in the sky. I know pilots are important, but you're not the only airplane in the sky. So the idea of having this random PRF is that your airplane remembers what it sent, and it listens for the same pattern coming back, and it goes, oh, that's me. And it will ignore all the other replies that are going out to other airplanes. So each airplane knows that that communication is for it because of the jittered PRF.
So it's not possible by any chance that the two airplanes...
It's random, it's completely scattered. So it just remembers what it sent. It's not like this airplane sends this pattern always and that airplane sends that pattern. The pattern that your airplane makes is forever changing. So the chances of that happening are very remote. Particularly as we'll get on and see, this can only talk to 100 airplanes at a time anyway. I suppose one day it will happen.
But then it would only happen on one occasion, wouldn't it?
Yeah.
And presumably it's going back and forth quite frequently.
It's constant.
Yeah.
So it would happen for that long.
Just make sure you like a different number for a second and...
You wouldn't even see it.
Yeah.
So we have side lobes. Do you remember side lobes? What do they do? What do they do? Side lobes?
Transmit outside the main beam.
They transmit outside the main beam. The problem is, some of the side lobes are going to come straight down to the ground. Hit the ground and go back up. What can you tell me about the pattern of those side lobes? They're the same as what you sent out. Your airplane is going to go, oh, that's me. It's going to go, oh, that's me, and it would go, all right, that's it, and you'd end up reading your height. So we need to stop that. And the way that it is stopped is that these transmissions coming back are 63 megahertz different. Removed is the word that they tend to use. Removed by 63 megahertz. They might be above, they might be below. Some are above, some are below. That means then that you're not going to take any notice of bounces back from cycles. So what happens, what we're trying to get is a distance, isn't it? So the aeroplane knows what it transmitted and when it transmitted it. And it starts timing. And it just waits to see how long it takes for that pattern to come back. So we now have a time. We know the speed of the radio waves travel, so therefore we can work out a total distance travelled. And we need to half that, because the total distance travelled is there and back, so our range is half the total distance travelled. That's pretty much DME. So DME, narrow spectrum, is that? Let's get rid of this before it sticks. It can only be line of sight because it is UHF. What frequency band is DME? UHF. Simple as that. You might be asked the frequency range. Not so likely, but you might be asked. They are paired with ILSs, with VORs. So if you've got a relatively modern aeroplane, you dial up your ILS, and if there is a DME associated with it, then it will be automatically dialed up. Of course, if you've got a modern aeroplane, you dial in your route plan before you even start, and the computer decides which radio aids it wants. So you don't do a lot. Two components to it. So there's the airborne interrogator, which is you and the ground-based touchscreen installer. So, I said it sends these pulses. The problem is this DME is talking to other airplanes. It can't talk to you and the other airplanes at the same time. So you have to find a slot that is empty. So your airplane shoves out a wodge of rapid pulses, hoping to find a vacant time slot. So it sends out 150 pulse pairs per second on average. Notice on average, it's not fixed. And it will do that for around about 30 seconds. So that's a bit like a little kid going to mum when mum is engaged in a fascinating conversation with her best friend. They're locked onto each other, and kid will come in, mum, 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 trying to get in and can't. So kid gets disillusioned and then starts, mum, mum. So they don't give up, but it's coming at a much slower rate. So then we go into, it's true, isn't it? We've all been there as kids. We've all been there as, well, not all been there as parents. Oh wait, shut So then it goes on to 60 pulse pairs, so the rate is more than half. Hopefully, eventually, we're able to lock on. She goes, eventually, yeah, and then sure, you've got your communication, and so we call that the tracking mode. And then clearly, once we're tracking, the rate of pulses can come right down, and it's around about 24 pulses per second.
So once you've got that slot, that's your
That's
slot.
yours now.
You can now talk to your mum.
That's yours. You've got attention, and that's your slot. And or any other timescales, obviously talking to all these other aeroplanes. So from that, then we get distance, and that's distance measuring equipment. That's what it's about. We can also get ground speed, assuming something. Not really.
Flying towards or
I've
away.
got to be flying directly towards or directly away from, and then we can compute the ground speed. The way that we used to do it, where we click the stopwatch for a minute and see how many miles a minute just ticked away in the minute, and then you've got speed miles a minute. Modern aeroplanes, of course, actually do that for you and give you a readout. It is possible that you lose that slot for a moment. So your airplane goes into memory mode. So it's still trying to bash out the communication. It goes into this mode, and that shouldn't last particularly long. While you're in that memory mode, it will still work out on forecast, if you like, about what the speed, what the distance should be. So it will keep giving the information based on forecast. Notice it's not true, it's just this is what should have been if nothing else has changed. After that, yeah, that's as ICAO states, it shouldn't exceed 10 seconds, but sometimes we know we've used this equipment, sometimes it does. Next bit is about how much communication the beacon can cope with. The beacons have to transmit 2,700 pulses per second, whether there's any aeroplanes around or not. This device, I think it's called a squitter in there, so if it's not talking to anybody, it will still push out this number of pulses, but they won't mean anything. That will limit how many aeroplanes you can be in communication with, because that is its limit, 2,700 pulses. Sorry, so that jumps out at, taking all the different rates that people will be having pulses at, it comes out as approximately 100 aeroplanes. And for those of you who have flown over France in particular, which is really busy, will probably recall that you've had times where you've had a lot of problem trying to get your DME to lock on because there's just too many aircraft around trying to use it. And it says there it will go to the strongest signal. The DME equipment, once it starts to realise it's getting saturated, effectively closes down its receiving ability. So it only receives the strongest signal. So it will start to weed out the weaker ones such that it's still communicating at the 2,700 pulses, which is its maximum. The strongest signal obviously means then, should mean the ones who are closest. But it doesn't necessarily mean the ones who are closest, because somebody might have a really strong DME, in which case you're going to get the attention.
Does it apply to new aircraft who are applying to lock? If you are already locked on the DME, you can be
You could get chucked off because it's this receiving capability. If you cut a new signal and there's a weaker one, then it will go to the the strongest.
Even if you are locked on.
And of course you go into memory mode then, hoping that you may be a bit closer and you can kick somebody else out. Examples of frequencies, don't get bogged down by this. It's just trying to illustrate this, the removal by 63 megahertz in interrogation and responses. So there's an interrogation at 1175, so reply will be on 1083. So that's what that's trying to show. And same thing there, just different numbers. So we get distance information, which is the prime thing. We can get ground speed, as we've said, provided you're going to and from. And that only works, of course, if you're going directly to or from the loop. So we're getting a change. Basically, it's all done on rates of change. How many miles per minute is it changing by? We get accuracy reduces, underreads the ground speed. So what are we talking about? Beacon, aeroplane. That's what measured, isn't it? We measure the slant range, as it's called. But we interpret that as being ground rate. Talk about our distance. So, and obviously, if that's a triangle, this is longer. The hypotenuse is always longer than the side. If I'm over here, then I've got the same situation. But of course, the further away I go, the closer the hypotenuse and in length than the side become. So the error, the difference between the two, is less. So it's more accurate at giving me a ground speed the further away I am. Clearly, if I were up there, it's rubbish, isn't it? It would be reading my height, even though my ground distance was 0. And if I were travelling, say, from there to there, just that distance, what would it give me in terms of distance or speed? It would say almost nothing, wouldn't it? Because the length of that is hardly changing as I go through that little range. So it would say that my ground speed was 0. So the closer we get to the station, it underreads. The further away we go, the more accurate the ground speed becomes. So questions we'll ask, obviously clearly the distance is one thing that's different. So 100 miles, 20 miles, which one's more accurate? Clearly that one is. How about though if you were given 100 miles but going towards, or 100 miles going away from? Which would give you the most accurate ground speed? Do we all agree? Away? No, we don't all agree away. Okay, so if I'm going to, let's say at the end of my timing, I've got to there, my average distance from the beacon is that. If I'm going away, so same distance, so my average distance from the beacon is that. So therefore, this one is going to be the most accurate reading.
What about the accuracy of the DME? It's not 1 point something like plus.
We're talking about ground speed accuracy.
Will be more accurate going to.
It's more accurate going away. Because distance is further, so you've got less error. slant range. That's it.
The accuracy of position,
Further
then
away from
this
beacon
could
you are,
be,
the more accurate.
Okay, just put it there.
Yeah.
in terms of ground speed, it's better. Are we all okay with that? So that's what that is returning. So the accuracy reduces or underreads as we get closer. So be careful of the ranges. So here's a question. That's easy actually, isn't it? So where are we going? D. Yeah, it's easy, isn't it? It's well separated, massive changes. All right, identities now. So when you use a beacon of any sort, you are required to identify the beacon. If they are used as a pair, like an ILS and a DME, they are given a common ident. We say that they are co-located beacons, and they share an ident. And in order to fit that rule for instrument approaches, the beacons have to be within 30 metres of each other. Otherwise, if you're using DME and a VOR, one's over here, then your range and the bearings are not going to quite tally up. So they need to be close together. If you're using it for airways co-location, then they only need to be within 600 metres of each other because the distances involved are much greater. Therefore, the accuracy doesn't need to be quite so tight. But for the ident, so we've got the Morse, and what we hear is that the DME will come once and the VOR will come 3 times. You need to know that you have both, of course. So the way that you can tell them both is that the DME tone is a slightly higher frequency. So you would have something like and so on. So you're getting the change in tone. You can go, okay, I know I'm getting both because they've both got the same ident. And supposedly every 40 seconds. In the comms exam recently, they asked at what rate should you speak? People just went, what? But apparently it is in the ICAO manual. Oh, I don't know. TACAN, so the military have a device called TACAN, which is very much like a combined VOR DME. As civilians, we don't have access to the VOR component of it, if you like, but we can use the DME element. So that's what that is about. So, come back to range. So you can see we've got the DME range, which is what we get. But it's not our ground range because the DME range is a hypotenuse and the ground range is a side, and you can imagine that people who write questions go, oh, okay, let's play with that, and so they do. You might remember Pythagoras. So sum of the squares sum of the square of the hypotenuse, the square of the hypotenuse equal to the sum of the squares of the other 2 sides. That's right, that's the way it goes. But basically, the slant range squared is equal to the ground range squared plus the height squared. So the slant range is equal to square root of, yes, just playing with the formula. Overhead the beacon, obviously, DME slant range will be equal to the height. We've said that already. So, there you go.
Sorry, can you just go back one page? Cheers.
Nearly dying. Yeah. Alex is using a lot of money on it. Did you come in here in summer? Anybody come in summer? Oh, it's a nightmare in summer. These two rooms get heated by the sun. The room down the corner doesn't get so but there is one detector for all three rooms. And people in here are boiling, and the people in that classroom are there freezing. I think this is where you're most likely to make your big mistake. Because you're very likely in the stress of the exam room to go, right, the answer's 24. Forgetting you need to take the square root of that to come up with nearly 5. And you know what, don't you? 24 is going to be one of the answers. So be careful. Whether what? Yeah, it's got what?
On the calculation, they've actually used my question.
Really?
Yeah, that's good. Yeah. Some of it rolls out. When I checked with the rules, and it's actually just
Okay, so what we get from DME basically is a, a range from the DME, and around the DME clearly that would describe a circle, and you could actually fly all the way round there, and that would read a constant reading on the DME. So it leads to a question. Which one are we going to go for? Sorry? B. B is the answer. Slant range and to the centre of the station, effectively.
The answer to the
Just
question bank is A.
Yeah, that's how we want
It should be slant range, that's what you should get. Are you telling me the question back is saying A?
A.
There's a thing about appealing it because there was an issue that schools teach one way but they
Yeah. What does it mean, line of position? So for reference,
The
that
line
would be
circle, that's your line of position. Distance from the DME.
Does it mean the position in space or the position on the ground? I don't know. If it's the position in space.
Well,
then
what you
science-
actually get from a DME, if you imagine that that was a DME, you get almost a sphere around the DME, because when you direct above it, you would read 5 anywhere around there. So on the ground, you get a circle. That's how we interpret it. It's been a sort of-
John, is that clearly slightly different for the ones that tell you you're at 0 at the threshold? You know,
Yeah.
so
That's,
they can just computer-wise.
oh yeah, this is just a normal one. Yeah.
Are those ones given a name or anything like that, or not? To say that it's offset to the threshold?
No, you'll just, if you look on a chart, it's that they're associated with approaches. I've just noticed something too. That's no longer Bristol. So we're ATP digital. ATP online. Used to be belonged to the school. But it doesn't anymore, because Alex, as a tax dodge, gave it to his wife, who then left him. Took the business with her. A very profitable part of the business. Okay, so we use DMEs all the time. Interesting one, perhaps this one. Is approaches, so we're with Gloucester, going into Gloucester here, coming in on this route. For instance, we're using a QDM 045 to go into the VOR, and then there's that point there with a D10, meaning 10 DME, so a combined VOR DME. Get to that point, and then we are flying, turning left and maintaining 8 DME. So it's quite an imprecise manoeuvre in a way, but you're going to fly and hold 8 DME as well as you can until you get to a QDM of 080 again for that beacon. So you're using your OBS, OBI for all this sort of thing, and all you're interested in is when you cross that line. When you cross that line, then you start a right turn, and then you need to change your deviation indicator OBS OBI thing then to give you the 094 to going on that track there. So you're changing your OBSI thing. Initially you're going in that track, then you've got to get that one up, and then you've got to get that one up, and you're setting this up as you progress through. So DME is all the way through. So DME going round that there, DME 8, DME 8, and so on. Another one coming in there. So we use DMEs an awful lot, especially with VORs. We get a range and bearing. We've effectively got a fix from that. It's really useful.
So to keep 8 an arc,
Yeah.
basically we just trial and error.
Yeah.
If we see we get close,
You
we
see
go
the
far.
number 8, and if it starts to move, then you tighten your turn a bit. If it starts to move the other way, then you slacken your turn a bit. So it's not a very precise manoeuvre as such, but it will get you where you need to be. And that place, look, there is no obstacles in that area anyway, so it doesn't matter. So the published accuracy. These are the figures, the top ones that are currently used in questions. So the bottom one I would largely forget, but you never know. You might be unlucky that this is the first time they introduce the new one. So it gives us a question. Are you going for A? A? I did there a B or a C or D or something over here. Hands up for A. Some doubt. A it is. So the maximum error could be the 0.25 added on to the 1.25, which would give me 1.5. The maximum error I could have. So 100 miles, my maximum error is 1.5 miles. And with the VOR, we saw at just 60 miles, our accuracy could be 5 miles. Way more accurate than VORs at distances. How about this one? Don't forget, it's a matter of time to do that, time to come back. My range is half the distance that the radio wave travelled. The first thing is, don't forget the 50 microseconds. You might or might not remember that a radar mile is 12.36 microseconds. So basically, that's the time it takes 1 mile to go there and back. 12.36. If you can remember that, I can never remember it. I would have to go from my 300 meters per microsecond and work it out that way and then convert it. It would be tedious, but that's the way I would do it. So all I need to do, if I can remember this magic number, is divide that one by that one, and that gives me 158 nautical miles. Don't get too worried about working things out in radio. There's generally plenty of time. You will walk out of the exam with loads of time spare.
How many questions are there?
I can't remember. I gave it to you on your sheet, one of your first sheets, the handout with where the questions are and how many there are. Not many.
Did you get 2 hours?
It's not 2 hours. Perhaps an hour and a half, maybe even an hour. What does it say on there? It's an hour and a half. But you've got loads of time. What do you need? Well, you need stuff for dialing it up, basically. explain it. What's the matter over there?
No, because I was trying to work it out with just the speed of a radio wave.
Yeah.
Over the time it took.
So the way I would have done it is I know that's 300 meters per microsecond. So I have done my calculation based on that. So you've got the time. So I'd have timed that. It would have, was it 1950 or something? I've forgotten now. But times that, that would give me the distance travelled. I'd obviously have to halve that for the range, and then that would be all in meters. I have to convert it to nautical miles. So it was 1850, if I remember right, 1852, wasn't it? I remember something like that. Meters to nautical miles. That's the way I would have done it. Because I cannot remember the radar mile.
Can we just have a look at the answers again, if that's all right?
Yeah, sure.
Because I've got 170. Yeah, I just use the speed a lot.
Yeah, that's what
Where are you halving this because of that calculation?
the radar mile.
Speed, distance, time.
The radar mile is it's 12.3 seconds for a radio wave to go there and back for 1 mile.
I know. Maybe I will. Yeah.
Yeah, that's true.
I get there. Yeah, but it's there. There's a delay of 50 microseconds, so that's not the time it took to actually do the travelling. 2000 minus 50 microseconds.
Right. 25
So, SS